Hey guys, today we're going to go ahead and review a problem from Chapter 5, Differential Equations of Fluid Mechanics. Problem we're reviewing today is problem 17, Continuity Equation for a Sound Wave. Let's go ahead and read the problem statement. A one-dimensional sound wave of wavelength lambda travels with a velocity c. The velocity and density can be shown to vary as these two equations below. For waves of small amplitude, A is much less than rho naught, derive an expression for the divergence of rho Vx and verify that the continuity equation is satisfied. Alright, now before we derive an expression for the divergence of rho Vx, let's go ahead and see if there's any simplifications we can make. Right away, the thing that sticks out to me is that A is much less than rho naught. And since A is much less than rho naught, we can go ahead and make a simplification of the density variation equation. Alright, so let's go ahead and rewrite the density equation. Rho equals rho naught plus A sine of omega times quantity x over c minus t equals, Now, since A is much less than rho naught, we can assume that A is negligible, which means it's 0. So this entire term is removed, is canceled out effectively, and that simplifies the density equation such that rho equals rho naught. Now, a couple things can be extracted from this simplification. Right off the bat, the first thing we can do is say that density is constant, and from this we can say it does not vary with time. So partial rho over partial t equals 0. The next major simplification we can make, as you can see from the velocity equation, is the fact that rho equals rho naught. So instead of rho naught being here, we can plug in rho. So let's go ahead and write the updated velocity equation. Vx equals ac over rho sine of omega times quantity x over c minus t. Now we want to make this update or kind of change to more generalize the velocity equation. Alright, from here let's go ahead and quickly touch on the topic of the divergence of the velocity vector, which is del dot v equals partial vx over partial x plus partial vy over partial y plus partial vz over partial z. Alright. Now, this is the divergence of the velocity vector, and this divergence can have a constant added to it. Or a constant can be added to the divergence of the velocity vector. So let's go ahead and add the constant rho. Rho del dot v also equals del dot rho v. Now, what we have just done is said that regardless of where rho sits within the divergence, whether that be outside of the dot product or within the dot product, it still results in the same thing, and that is the updated divergence of the velocity vector, partial of rho vx over partial x plus partial of rho vy over partial y plus partial of rho vz over partial z. Now this equals 0. Now the next thing we're going to try and do, let's go ahead and actually rewrite that equation real quick. Partial of rho vx over partial x plus partial of rho vy over partial y plus partial of rho vz over partial z. Now, if we go back to the problem statement real quick, we can see that the sound wave is one-dimensional. And from the velocity variation equation, we can see that that one dimension is in the x direction, which means that we can go ahead and write that velocity equals vx and assume that velocity in the y direction and velocity in the z direction both equal 0. From here, we can simplify this equation and remove this term, or cancel out this term and cancel out this term. That updates the divergence of the velocity vector with rho added to it, or it basically just updates this equation to partial of rho vx over partial x equals 0. All right. Now, from here, we can go ahead and start plugging in what we know. Now, the first thing that we obviously know is the updated velocity equation. That's right up here. So let's go ahead and plug that in. I'm going to go ahead and grab a new sheet real quick. Okay, now with both what we know from over here from this equation, let me go ahead and pull that over. Partial of rho vx over partial x equals 0. Now we're plugging in the updated velocity equation right here. So partial over partial x of rho times the velocity equation, AC over rho sine of omega times quantity x over c minus t equals 0. Right away we can see that the two density terms cancel out, which leaves us with the remainder of the terms. And that ultimately equals 0 as well. After taking the partial derivative, that gives us omega over c times AC sine of omega x over c minus t equals 0. We can also see from here that the c's cancel out, and that gives us the final derived expression for the divergence of rho vx, which is a omega sine of omega times x over c minus t equals 0. All right. Now that we have derived the expression for the divergence of rho vx, let's go ahead and verify the continuity equation. For starters, let's write down the continuity equation, which is partial rho over partial t plus partial of rho vx over partial x plus partial of rho vy over partial y plus partial of rho vz over partial z equals 0. All right, let's see if there's any simplifications we can make. Now, looking back at some of the earlier simplifications we made when deriving the expression for the divergence of rho vx, we saw that density was constant, which led to the fact that it didn't change with time. Now, since it doesn't change with time, that means that we can go ahead and cancel out this term. That term is now 0 from here. And we also saw that since the sound wave is one-dimensional, and that dimension being the x direction, there is no velocity in the y or z directions, which means that we can cancel out this and this. This simplifies the equation to partial rho vx over partial x equals 0. All right, from here, we can go ahead, since this looks quite similar to what we had right up here when deriving the expression, we can go ahead real quick and plug in the updated velocity equation. All right, partial over partial x of rho times AC over rho sine of omega x over c minus t make sure to close all the brackets there. I don't think I did up here, but let's go ahead and move on. Okay, right away, once again, we can see the density terms cancel out. Partial over partial x of AC sine of omega times quantity x over c minus t equals 0. After taking the partial derivative, that gives us omega over c times AC sine of omega times quantity x over c minus t equals 0. Right away we can see that the c's cancel out, giving us the equation a omega sine of omega x over c minus t equals 0. This right here is the final equation that we get out when verifying the continuity equation. And we verify that the continuity equation is satisfied from the fact that this equation down here equates to that right there, which is, from the problem statement, the derived expression for the divergence of rho vx. All right, guys, that's all for today. Thank you for watching.